All right, good afternoon, everybody. Thanks. Let's get started. The quicker we get through this, the quicker we can get to lunch. So, I finished the last lecture putting up on the board the Gaussian integral. I suppose many of you will have gone away and looked this up by now or come across it in some other context. But the Gaussian integral is an important example of doing a coordinate transform from plain Cartesian coordinates to plain polar coordinates. So we'll go through it briefly now. And then after that, today's lecture is going to be split into half. We're going to have half the lecture on the gradient, which I know you've already come across in the lecture on magnetism, but we'll derive it and hopefully give you a bit more insight into it. And then I'm going to do the second half of the lecture as a brief introduction to statistical distributions. So the Gaussian integral is the integral across the entire real line of the function e to the minus x squared dx. And if you look at that function like that, there's no immediately apparent way to solve this. However, the way that you can do it is by squaring the function, switching to plane polar coordinates, and in that way you can get an answer. So this is the integral of this function across the entire real line. If I then square this integral, then what I'm doing now is I'm integrating this function, or I'm integrating the square of this function across the whole of two-dimensional plane. So what I have now is I'm integrating between minus infinity and plus infinity, and minus infinity and plus infinity, e to the minus x squared plus y squared. I've just multiplied together e to the minus x squared and e to the minus y squared and combined them like this. And that would be a two-dimensional integral in dy and dx. Now the trick here is to switch this into plane polar coordinates. So what you can see here is that you are integrating over a plane in two-dimensional coordinates where the plane extends as a square to infinity in all directions. If I switch this integral to plane polar coordinates, then what I'm doing is I'm integrating over a circle which extends through the full 2 pi radians and extends to infinity in all directions. And because you're going to infinity, the fact that formally these shapes are slightly different doesn't matter. So then my square of my integral becomes the integral of my azimuthal angle. And again, remember that I will interchange without warning the azimuthal angle when I'm doing plane polar coordinates, theta or phi, and variously in different textbooks and sets of notes, you will see theta or phi when people are talking about plane polar coordinates. So the phi is just the azimuthal angle then, so that just goes around to the full 2 pi. So theta goes between 0 and 2 pi. And r goes between 0 and infinity, so that's the radius of our circular area extending out to infinity. So switching to these plane polar coordinates, x squared plus y squared, I see is r squared. So this is e to the minus r squared, and I'll be integrating with respect to dr and d phi. But I've missed something here, and that is the Jacobian for the transform from plane Cartesian to plane polar coordinates, and that's what makes the integral solvable. Okay? So I put in this term here, and this is my Jacobian. And now this is a relatively straightforward integral to evaluate. So this part here, I know is just going to come to 2 pi. And this part here is the integral of e to the minus r squared. That would put a minus 2r over there. So that's going to give me that between 0 and infinity. And that's going to give me plus a half. And so I see that my integral squared is equal to 2 pi times a half, so that's just pi, and so the Gaussian integral is the square root of pi. Okay. So that's a very well-known example which you should be able to do on request at any given point, and illustrates the importance of using the Jacobian in transforming from plane Cartesian to plane polar coordinates. Okay, good. Okay, so now we're going to talk about the gradient, and I know, as I've said, that you've already had this introduced to you in electromagnetism. That's an unfortunate consequence of the way the lectures are scheduled, but we'll go through its derivation perhaps in a bit more detail now than you've seen previously. There we go. Right, so the first thing to know, and this is a fundamental point for all of div, grad, and curl. Okay, so remember, there are these three unusual new functions which you haven't come across before in your A-levels, div, grad, and curl, and they all can be very simply memorized. You can memorize them all individually, or you can just memorize them by remembering exactly what it is that del stands for. So del, and this symbol is also known as nabla, is a vector operator. And it equals I, so that's the unit vector in the x direction, times the partial derivative with respect to x, and similarly for the y and z directions. And you will see that gradient is the operation of del on a scalar field and transforms that scalar field to a vector field. The divergence is the dot product of this operator with a vector field and takes a vector field and gives you a scalar. And the curl is the cross product of this vector operator with a vector field and returns you another vector field. All you have to do is quite literally remember the form of this and remember that you're either taking it as a scalar action on a scalar field, as the dot product on a vector field, or as the cross product on a vector field, and you can always remember the notations for div, grad, and curl. A side note here, and it's something we'll return to in the next lecture, these are very straightforward forms for Cartesian coordinate systems. Okay, when you move to cylindrical or spherical polar coordinate systems, which we will come back to, then the forms of div, grad, and curl are a little bit more complicated, but I'll show you a very straightforward way to work those out. Okay, so then the gradient is the operation of this vector operator on a scalar field. So the gradient of some scalar field u, and I may use u, I may use phi, I may use some other symbol to illustrate or to represent my scalar field. If it's not underlined, it's not a vector, it's a scalar field. So that will be simply I du dx plus j du dy plus k dz. So what does the gradient mean? What the gradient means is it tells you the direction of and the magnitude of the rate of greatest change in your scalar field. So remember, your scalar field, in this case a three-dimensional scalar field, you can just imagine as a volume, and where at every infinitesimally small point in that scalar field, there is a numerical value, which represents the value of the scalar field at that point. And those values change, or in a particular peculiar case they wouldn't change, but those values change, and they change differently in the general case in each of the x, y, and z directions. The gradient, as we'll shortly see, it tells you the direction of the rate of greatest change of the value of the scalar field, and it tells you the direction in which that change occurs. So imagine I'm somewhere in my three-dimensional scalar field. So I have some three-dimensional scalar field, and I'm at some point x, y, z in this scalar field, and I move some small distance in the scalar field. What is the change in the value of the scalar field as I move in that direction? So the change in the value of my scalar field I'm going to call du, and that is simply dx, the amount I moved in the x direction, times the rate of change of the scalar field in the x direction. And again, similarly, for y and for the z directions. So what we can see now is that change in the value of our scalar field is equal to the dot product of the gradient with the vector which describes this motion in this scalar field. So I'm going to call this little vector, which represents my motion between two different points in my scalar field, I'm going to call that dl. The gradient is given by this, and if we dot product that with the small amount which we change in the x direction, plus the small amount which we change in the y direction, plus the small amount which we change in the k direction, where this then, this vector I'm dot producting here with is the dl in my sketch. That's the vector which represents how far you've moved in your scalar field. Then I see that the dot product of the gradient with this dl equals du. Okay, so this I've said, and then I've already said this, the gradient takes a scalar field and it outputs a vector field. And this is what I'm saying now. And note that you'll see in my notation, in my notes, and also on this slide, that I've interchanged these vectors and again, you should be familiar that when you see a problem, if you know the names of the x, y, and z axes, then this is, of course, just a unit vector in each of those directions. Since there is a tradition that the x, y, and z direction unit vectors are called I, j, and k, then these are completely interchangeable. So we can see that the magnitude of the change du is equal to the magnitude of the gradient times the magnitude of my little movement vector dl in my scalar field times the cosine of the angle between them. Just your standard definition of the dot product. And therefore we see that if you move in your vector field in the direction of the gradient, then you get the maximum change in the value of your scalar field. So my scalar field has some value here. I can move in any direction I like. If I move in the direction of the gradient, then I get the maximum change in the value of the scalar field. And if I move perpendicular to the direction of the gradient, then I get no change in the value of my scalar field. And what that in turn implies is that gradients are perpendicular to equipotentials in my scalar field. This then in turn means that you can use the gradient to calculate the normal to a surface if, as you always can, you can describe that surface as an equipotential of some scalar field. So let's have a look at, oh wait. Well also, so there's a very straightforward example which you'll have already come across in electromagnetism, which shows you clearly how you get field from a potential, and that is that the electric field is minus the gradient of the electric potential. And similarly, the gravitational field is minus the gradient of the gravitational potential. And this I've already said. Okay, so that's the change has a maximum value when it is in the direction of the gradient, and its rate, the rate of change, is the magnitude of the gradient. So we'll return to the example of the electric field in a moment, so I just want to show you a couple of visualizations. So if you imagine that you had a two-dimensional scalar field, so a scalar field in x and y, which is illustrated here, so the value of the field at some given point in the x and y coordinates is just given by the height of the function here. This could be, for example, the height of the terrain on a map. So this could look like this. So this could be some two-dimensional scalar field. If I viewed it from above, then I would have these coloured contours like I have here, and those are equipotentials. Those are points of equal height, just like the contours on the contour map. If I calculate the value of the gradient on, for example, for this two-dimensional scalar field, some examples of it are plotted here. So you can see that the magnitude and direction of the gradient are given by these arrows. And in regions where the curvature is not that strong, then the gradient is not very steep. In regions where the gradient is, the curvature, where the rise is very large, the gradient is large. Okay, so in a very intuitive sense, if you just think about the height of a terrain, it's obvious what the gradient means. And the gradient always points in the direction of the greatest increase of the scalar field. Okay? And this, again, points to the reason why the electric field and the gravitational field are the negatives of the gradients of those potentials, because you know that things always move to lower energy. Okay? So we need the definition, given the definition of the gradient, we need the negative sign in there to illustrate the value of the field and how something will move under force in that field. So then, we have an example, the gradient of the electric potential. So the electric potential is this. If I put it into x and y Cartesian coordinates, then I can say that the electric potential is given by this. And then I can work out the gradient of the electric potential in order to work out what the electric field is. So the gradient of the electric potential then would be C I of this differentiated with respect to x, which is going to be minus a half times 2x all over x squared plus y squared to the 3 halves, plus j, and similarly minus a half 2y all over the same denominator. And this then is going to be minus c I plus j all over that expression. So that is a vector. You can see, you remember you did the sketches of vectors for the last lecture. This is a vector field which always points towards the origin. This is a radially symmetric case. One of the powers of a half here, so this is the radius to the point cube. One of the powers of a half here is just normalizing the size of the vector to make it a unit, and then the other two powers of a half represent the 1 over r squared fall off in the potential. And you can see that this is a vector which points back like this, and whose strength falls off at increasing distance from the origin. And because the electric field is the negative of this, this means that the electric field points away in the opposite direction to those. Now, you can also more simply calculate the electric field by doing the following. You can say, okay, I'm going to represent the electric potential as some constant over R. Okay, and if I then just differentiate with respect to R, then I get the same answer. Then I get that my electric field, that the gradient of the electric potential is going to be minus C, some unit vector, in the radial direction to the point, that's a unit vector over R squared. And you can just do that by applying the same rule, but switching out your x and y for R. So you may think that's all you do. All you do is change your coordinates. But beware, okay? This only works in this case because the electric field and the electric potential have a radial symmetry, so you only have to consider it as with respect to R, okay? Once you start introducing things which have angles in them, then you will see that the terms in the gradient and also in the divergence and the curl are not simple analogues of the x, y, and z terms, and we need to actually calculate the expressions. So don't think just because this works that you could do a similar replacement for a field that also had a variation in phi. And this is of course, then what the gradient of the electric potential looks like. So this is the electric potential. This is the gradient of the electric potential. This is what the potential looks like as a 2D scalar field, where the height is the value of the scalar field. And if I calculate the gradient at each point and look at it from above, then I can see these arrows here indicate the direction of the gradient. Again, the lines represent equal contours, and you can see that the equal contours are circularly symmetric, as you'd expect in this case, and that the gradient is perpendicular to the equipotentials, okay? So when you can describe one of those equipotentials as a surface, you can use the gradient to work out the normal to that surface. Yes, and as you know, the electric field is the negative of the gradient of the electric potential, and analogously, the gravitational potential and the gravitational field. Okay, so let's do an example of using the gradient to work out the normal to some surface. So we want to work out what is the normal, the perpendicular to the surface given by x squared plus y squared minus z equals 0 at some particular point. And what we will do is we'll work out the general expression for the normal, which will be a function of x and y and z, potentially. And then we will calculate the specific value. So what we can do is that we can say, okay, that surface there, that's just an equipotential of some three-dimensional scalar field, x, y, z equals x squared plus y squared minus z, in the particular case, or equals 0. So it's an equipotential of this field, so I know if I work out the gradient of this field, the direction of that gradient is going to be perpendicular to this equipotential, and that's going to give us the normal to the surface, which is what we want. So the gradient of my scalar field is going to be 2x in the I direction plus 2y in the j direction minus k. Now, that is a normal to the surface. I want a unit normal to the surface, so my unit normal is going to be 2xi plus 2yj minus k, divided by the magnitude of that, and the magnitude of that is going to be the square root of 4 plus 4 plus 1, which is 3. So that is the unit normal to the surface described in the question. done by taking the surface as a scalar field and calculating the gradient. Of course, remember, obviously,
What
yeah.
about x and y in the length?
Sorry?
In the length, it depends on x and y as well.
The denominator should have an x and a y.
Yeah, you're right. My apologies. So, first off, what I should do is I should remember that we're evaluating this at 1, 1, 2. Okay. So, at 1, 1, 2, this becomes that, which is rather convenient for this question. Thank you very much for spotting that. Which then, in fact, reduces to this. Hmm? The minus k is there, isn't it? Right. Right. So this is a unit normal to this equipotential surface at the point 1, 1, 2. And of course, remember that the negative of this vector is also a unit normal to this equipotential surface. Okay, so let's have a look. Let's try and visualize what this actually means. So this is, so I said that we could consider this to be a scalar field, u, x, y, z, which has the value x squared plus y squared minus z. So what I've plotted here is this scalar field, u, x, y, and z. Or written it as f, x, y, z. So this is the value where the value of the scalar field at a given point is represented by the colour. Okay? So this is my scalar field, and I can clearly see that I have strong positive values of the scalar field here, and I have strong negative values of the scalar field here. So this gives you some sense of how the gradient would operate if I was calculating it for this scalar field. So the gradient in this case would be operating to take you from regions of negative values of the scalar field to regions of positive value along the direction of the greatest increase. So, where is this surface then of x squared plus y squared minus z equals 0? So I can also plot this surface, and of course you'll have noticed that I can also just consider this surface to be a two-dimensional surface as a function of x and y. Since we have a 0 there, it's easy to do the substitution. So that's what that two-dimensional surface looks like, which is a surface in the three-dimensional scalar potential. And if I plot that on top of my scalar potential, then this is what it looks like. So again, the colour scheme is the scalar potential, and now this surface here equals the surface which corresponds to this scalar field equaling 0. So what we have done is we've calculated what is the general function for the unit normal, or for the normal perpendicular, obviously, to this surface at some point, and then we've calculated it for a specific point. And in this particular case, you actually end up with a whole bunch of nested surfaces, since this is just a function of x squared and y squared. Okay, so that's it for the gradient. We'll of course return to using the gradient in some more detailed examples later on in the course. But you've already been using it in electromagnetism, and now you know where it came from. All right. So completely switching tack and switching directions then. This is a component which was added to the course just a year ago. So as I've mentioned earlier, this is a component which you won't see many examples of in the previous papers. And what I'll do is when I do the revision lecture next term, I'll spend some time going over the statistical distribution questions which were on last year's papers, both the June and September papers, so that you get some idea of the kind of things that you might get asked. And the reason this component was introduced to the course is that in the second year, you go straight into physics courses where the concept of the probability density function and the cumulative distribution function, that is the PDF and the CDF, are assumed. Your knowledge of these are assumed. So it was important to give a little bit of background. Okay, so here's a really dopey, simple question, which will illustrate some of the points that we're talking about. So your friend tells you she'll stop by your house sometime after or equal to 1 p.m. and before 2 p.m. But she cannot give you any more information as her schedule is quite hectic. So when again, you know, the art here is reading the words of the question and trying to work out what that means mathematically. So when it says cannot give you any more information, that's going to tell me there's going to be a flat distribution of probability of her arriving between 1 and 2 p.m. Your friend is very dependable, so you're sure she will stop by your house in this time integral. So that tells me that's the complete extent of my distribution or density function. Okay, and the probability of her arriving between 1 and 2 p.m. is going to be 1. But other than that, you have no information. We assume the arrival time is completely random in the interval 1 to 2 p.m. So first one little thing, you'll notice that the question says after or equal to. So that is that, whereas the end time just says before, and we use these two symbols for probability distributions to illustrate those two criteria. What is the sample space S? Well, the sample space in this case is simply where these are hours PM. It's important to be consistent with what your units are. Sketch the probability density function and the cumulative distribution function in these two cases. So this is what we're going to do. Here on my x-axis I have time, and I'm going to have 1 p.m. here, and I'm going to have 2 p.m. here. And we know that this friend is going to arrive between 1 and 2 p.m., but we know that we don't know anything else about the probability of her arriving in that interval, so we're going to assume that there's a flat probability distribution between the two. The probability density function is denoted as fx, like this. So this tells you it's a variable in x, and this tells you that we're actually going to describe it in terms of varying values of x. Now that is the probability of her arriving in some given interval. And we know that there is no chance she's going to arrive before 1 p.m. or after 2 p.m. So the PDF before 1 p.m. and the PDF after 2 p.m. are 0. And we know, therefore, that the probability of her arriving between 1 and 2 p.m., as I said, is a flat function. So this is the PDF. That is the probability density function of my friend's arrival time. They're arriving between 1 and 2 p.m. We can't illustrate when we draw this the fact that 1 is greater than or equal to and 1 is less than. That's the PDF. Okay? The total integrated area of the probability density function has to be 1, and that's how you normalize it to work out what some of your constants are when you calculate the PDF. And that means is that the probability has to be 1. It has to be that she will arrive sometime in this interval. The cumulative distribution function is the probability of her arriving up to some time. Okay, and I'm going to illustrate this with a yellow piece of chalk. And this is the integral of the PDF from 0, or from the bottom of my range, up to the time in question. So again, the total chance of her arriving before 1 o'clock is 0. But after 1 o'clock, the chance that she has arrived increases. And if I do a separate axis here, which is my CDF, so that's the CDF, and this one is the PDF. by 2 o'clock, the value of this should be 1. This is the total integrated probability. She must have arrived by 2 o'clock. And you can see very clearly that this is because this is just, this is an integral of a flat function. This is going to be a linear increase. And that is what the CDF looks like, okay? So it rises linearly until you reach the last time she might possibly arrive, by which time it should have reached a value of 1. Okay. And what you can see, therefore, is that the PDF, the probability density function, which we denote like this, is the gradient of the cumulative distribution function. In the case, which will be the case for pretty much every example you come across, that the cumulative distribution function is differentiable. Okay, so there are some other questions here. So the question says, what is the probability of her arriving when the time is exactly 1.5? Okay, when the time is exactly 1:30. So the probability of her arriving when the time is exactly 1:30 is 0. Okay? Because you can only evaluate the probability of you can only evaluate the probability of something happening as a range in the PDF. Okay, so you could only say, because your time intervals can be infinitesimally small, the chance of arriving at any particular time, or the chance of a variable taking some exact value, is 0 for continuous probability distributions. There are also discrete probability distributions where this can be, you can actually have specific values. So the probability of something happening in some interval actually has to be the integral of the PDF between an upper and lower limit. The value at some precise point is 0. And that's implied by the fact that you have density in the name. What is the probability of her arriving in the interval between 1 and 1:30? So if I go back to here, then you can see this in a couple of ways. So if this is 1:30, which I've illustrated by 1.5 in the question, then I can say, okay, what's the probability she arrived in here? And I can clearly see that the area, the total area here, is half of the total area. So the chance that she arrived at 1:30, unsurprisingly, is 50%. I could also have read that off from the CDF, which will reach a value of 0.5 here. So that's very obvious as well. And finally, if I have some arrival time A, if I have some interval of her arrival time between A and B, where A is greater than or equal to 1 and B is less than or equal to 2, what is the probability of her arriving in that case? So what you want to do there's a range of ways of doing this. You actually want to work out what the height is of this here. Okay. And again, it depends what units you've used, but if you're using the units of hours, then the height here is 1 per hour. And that basically means that if you integrate over this 1 hour interval, then the probability of her arriving in that interval, as you know, is going to be 1, because there's only a 1 hour interval over which she can arrive, and our units are hours. So this then means that the probability of her arriving in some interval AB, in this case, is simply going to be B minus A. Okay, right, all right, that was the boring but straightforward introduction. There's some other things that you need to be able to evaluate for these statistical distributions. So the first one is you need to be able to evaluate the expectation value or expected value. So if I have some PDF, small fx, the expectation value of x, which is often written like this, is going to be the integral over my sample space of x times the PDF some function g of x, then the expectation value of that function, so remember, we have an fx, we have a PDF, which describes the likelihood of x taking some value. In order to work out the expectation value, or the mean value of some function of x, we have to perform the integral of that function multiplied by the probability of x taking that value over the whole possible range of x. So again, this would be integrated over the sample space, g of x times fx of x dx. So do we have an example? Okay, so here is an example then, a very straightforward example. Find the expectation value for the PDF equals x plus a half for the range x is less than or equal to 1 and x is greater than or equal to 0 and 0 otherwise. So in order to work out the expectation value of this function, what is the mean value of this function, given that I have this distribution, sorry, I haven't said what the function is here. This is the probability distribution function, and we want to work out our function g of x is x to some n. What is the mean value, or the most likely value of this x to the n over this probability distribution? So the expectation value of x to the n is going to equal the integral over the sample space, and in this case that's between 0 and 1, of x to the n times my probability distribution, my PDF, which is x plus a half integrated with respect to dx. So that equals x to the n plus 1 plus x to the n over 2. So this then equals x to the n plus 2 over n plus 2 plus x to the n plus 1 over 2 n plus 1. Integrated between 0 and 1, which equals 1 over n plus 2 plus 1 over 2n plus 1. Which you can straightforwardly rearrange to give you 3n plus 4 over n plus 2 times 2n plus 1. So that is the mean or most likely value of the function x to the n when my probability distribution is in the range 0 to 1 and has the form x plus a half. And in this way, you can work out the mean value or expected value of any function given the probability density function for the variable in question. One of the other things that you'll need to know is you'll need to know the variance. This is a very common expression. The variance, which you'll use to work out the error on things later on in your degree, is the expectation value squared minus the mean value squared. So let me just show you a few examples of typical probability distribution functions. So a top hat probability distribution function, like the one we were talking about in the example of the friend visiting, is of course just something which is a box shape. The integrated area under the PDF always has to be 1 if we're plotting the entire sample space. Okay? So you can see that as I make things wider, they need to get lower in order that the total area of the integral is 1, and the CDFs vary like this. Okay? They always have to reach a value of 1 by the time the PDF stops. So that's a very obvious case. This is the exponential distribution, which you come across sometimes in physics, which has this form, and in this case, the normalization is such that if you have something which falls off more rapidly, then it starts off with a higher value, and if you have something which falls off more slowly, like this one here, then it starts off and again in order that the total area under the probability density function equals 1, and the shape of the cumulative distribution functions looks like this. The most important probability density function, which you'll come across in physics and indeed in science, is the Gaussian distribution, which is also known as the normal distribution. This is the form of the Gaussian probability density function. Now you'll flick your minds back to the very start of this lecture where we did the Gaussian integral, and you'll see the connection between these. The probability falls off essentially with some constants in here. These are all constants. Everything except x is a constant. It falls off as e to the minus x squared, and it has some constants in front of it. The 2 pi, or the pi term here, actually comes from the normalization of the Gaussian integral, which we calculated at the beginning of the lecture. Okay. This is the most common form for the error, or rather, this is the most common form for the sample distribution when you're making measurements in physics. And what's more, there is a theorem called the central limit theorem that says, actually, if you are measuring some variable which itself results from a combination of many other variables, but you can only measure one of them, then in nearly all cases, your resultant probability distribution, probability density function, which you will use for calculating your errors, will actually end up converging back to a normal or Gaussian distribution. Okay? So it's the most important distribution in physics and the whole of science. Okay, and then finally, there is the case that sometimes you will want to do what is called making the marginal distribution of some two-dimensional probability function. So I may consider some two-dimensional probability distribution. So now this is some function, I should use the same notation. This is a probability distribution function, which is a function of x and y. So what that means now, if this is my x and y plane here on the bottom, then this is my f of x. And if this is my two-dimensional x, y plane, then for each value of x and y, my probability density function has some value, which will look like some surface if I were to sketch it. So you will sometimes be asked, what is the probability actually that x is in some range and y is in some range? And that just becomes a two-dimensional integral version of the integrals, which you can do very straightforwardly. So, for example, if this range is 0 to 1 and this range is 0 to 1, and you have a question asking you what is the probability that x is less than a half and y is less than a half, and you do a two-dimensional integral of this region. It's very straightforward. So sometimes you're asked for this thing called the marginal distribution, and what the marginal distribution will do is it will say, okay, we have, say, a two-dimensional distribution. Here is a bunch of measurements. So these are measurements which have been made in some physics experiment. I'm going to say that the Gaussian shape here at an angle is the probability distribution function, probability density function, underlying these measurements, okay? So if I could measure x and y, then I could actually know what the probability density function was and measure it f. But often in some experiment, you can only measure one of these variables, and then in the limit that you have a large number of samples, then you just need to, you can only measure what it is in one of the variables. So you can calculate from your underlying two-dimensional distribution what your distribution is in only one of the variables. So if you look at this distribution here and I project it just down onto the x-axis, what I've done is I've integrated, in order to make the marginalization in x, I've integrated over the whole range of y, and that gives me this probability distribution here, which you can think of as being this 2D distribution projected onto the x-axis, and similarly onto the y-axis. And so if I have a two-dimensional probability distribution, last line, the one-dimensional or the marginalized version is the integral over, over the whole of the sample space of my two-dimensional function with respect to dy. So I've integrated along all the dy's to get something which is only now a function of x, and similarly for marginalizing in terms of y. And we'll stop there, and I'll see you on Thursday morning. Thank you.